Hi all, my name is Blanca and I'll be discussing my poster, Searching for Dark Matter at ATLAS. ATLAS is one of 4 main detectors located at the Large Hadron Collider in Geneva, Switzerland. It accelerates protons to nearly the speed of light. They collide and the decay products of these collisions are analyzed. So dark matter is roughly 27% of the universe. It's not the same thing as black holes. It's not antimatter. It doesn't interact with light and it doesn't hold an electric charge. One idea of what this dark matter could be is something called a dark photon. This idea favors symmetry in the standard model, and through kinetic mixing, would be able to oscillate between the dark and the regular standard model photon. But if dark matter doesn't interact with light, how do we experimentally observe it? As mentioned, we're studying decay products of collisions. The idea being that you would record all decay products of known collisions. So energy in must equal energy out. If we do this and something is missing, conservation of energy says it can't just disappear. We therefore attribute this missing energy to something that can't be detected by our system, that is dark matter. So with all types of collision processes available, how do we pick one to observe? We select something relatively rare and simple. Higgs production is rare, and in particular, the ZH decay is useful because its decay products are simple to identify. Especially useful is this decay of the Higgs into 2 photons. Each of the photons should have half of the mass of the Higgs, which is 125 GeV. So if one of these photons were to be dark matter, the missing energy in the system would be half of the Higgs mass. Here we have 2 theoretical plots of transverse momentum and energy of these decay channels. Background signals of similar decays have lower energy and fall off more steeply. In particular, we're looking at the ZH decay in red, which is where we would have those 2 photons around the 60 to 65 GeV interval, again, half the Higgs mass. So when actual data from the LHC runs is plotted, you would want it to fit along this curve, showing an excess of missing energy along this interval. However, initial analysis shows that all momenta and energy in this specific decay channel are accounted for. But that doesn't mean the dark photon doesn't exist. It simply puts limits on future search conditions. So we can continue to search using different criteria, such as a heavy Higgs mass, something above 125 GeV, or looking at a different decay channel. We will also continue to search using higher luminosities of the LHC in future runs. Thank you for listening.